Hello, ladies and gentlemen. We have quite a lesson today. So, you're going to want to have your periodic tables handy, ready to write on would be nice if you have a paper copy. If not, you might want to have a piece of paper handy to write down the other way of doing it without your periodic table. So, strap yourselves in. This is going to be a long one. Here we go. Electrons. We are talking about the arrangement of the electrons in the atoms in section 4. So these are electron configurations we talked about. They're going to look very confusing, but they're really not that hard. You're going to have levels, sublevels, orbitals, and we'll have spins, okay? So this will be the kind of thing, once you learn how to do it, you'll look really impressive, even though it's really not that hard to do. So we first need to talk about quantum numbers. So we've got the shape, size, and energy of each orbital is a function of 3 quantum numbers, which describe the location of an electron within an atom or ion. So we're basically like giving each electron its own address inside the atom. The first number is the N principal energy level. On your periodic table, this is going to be like the level that it's on. And then there's the orbital, which is going to be the shape of the orbital. And then there's the magnetic suborbital. And the fourth one is derived from the wave function. That's going to be the spin. So we'll get more into that in the next section, but not today so much. Today, we're going to talk about the Pauli exclusion principle. If 2 electrons are in the same, no 2 electrons cannot occupy the same space at the same time. Sorry. And if they're in the same orbital, they must be repelling. So that's where the spin is going to be different. But today's focus is the Pauli exclusion principle, which says no 2 electrons within an atom or ion can have the same 4 quantum numbers. So they can't occupy the same space at the same time. If they are in the same energy level and the same sublevel and orbital, then they must repel each other. That's why you'd have opposite spins. So you can think of the 4 quantum numbers as an address. Like if I were going to write you a letter, I'd have to know your country, your state, your city, your street, your apartment number if you have that. So to get that letter to you. So we are going to have a little address for each electron in an atom. So let's talk about energy levels. Do you have your periodic table in front of you? Hopefully you do, and you can write these things on there. So each energy level has a number called a principal quantum number. We use the N to signify that. So N could be 1 through 7 because there are 7 periods on the periodic table. Oh my goodness. So if you have your periodic table, you might want to write these numbers out to the side. This is energy level 1, 2, 3, 4, 5, 6, 7, etc. Okay, so 1, 2, 3, 4, 5, 6, 7. You might want to go ahead and write that on your periodic tables. Then each level is going to have its own S. Now, when we talk about 1s versus 2s versus 3s, the difference is the size. So 1s is just a small one right there close to the nucleus, and then the second energy level will be bigger. So this guy is inside this guy, which is inside this guy. So remember, the goal is the electrons want to be as close as they can get to the nucleus. But the first level only has an S. It can only hold 2 electrons. Once it's full, you have to go up to the second energy level. So the next 2 electrons are going to have to go in here. Types of orbitals. So S is not the only one. So far we have S, P, D, and F. Could there be more? Sure. We just don't know of anything that has more electrons than we see on the periodic table, 100 or so. So we haven't had to deal with anything else. But in theory, there could be G's or whatever out there. So far we have 4 of those shapes. No more than 2 electrons are assigned to an orbital, and if they're in the same orbital, those 2 have to have opposite spins. So we'll call it counterclockwise and clockwise. You may say spin up or spin down. So here are types of orbitals. The first type, this is the S. It's just a sphere. So what are these coming from again? Remember our talk in the meeting. The orbital comes from those wave functions. It's just a probability. You have a 90% probability of finding the electron somewhere in this area, right? And when you plot out the p wave functions, you get this sort of dumbbell shape. And the d ones have this sort of clovery, I guess you might say, looking shape. So that's an S, a p, and a d. Now, the p orbitals have 3 suborbitals because you can orientate them on different axes. A sphere, you can't do that. No matter how you turn a sphere, it's still a sphere. But with the p orbital, remember you have a node. These are wave functions, so you have this node in the middle where no electron can exist here. And this is again where that people get uncomfortable. You're like, okay, well, the electron could be here or it could be here, but it can never be in here. How does it get from here to there if it needs to? So you again have, your things that don't seem as intuitive. But remember, there's the node where the nucleus is, and that you have 0 probability of finding an electron in the nucleus. So you can rotate these, though, on the X, Y, or Z axis. So here's an example of that. You have one on the X, one on the Y, and one on the Z. Each one of these sublevels could hold 2 electrons. So 2 electrons could go here, 2 electrons could go here, and 2 electrons could go in here. So a P can hold a total of 6. 2, 4, 6 electrons in total. An S can only hold 2 because you can only put that sphere in one direction. Or, well, it doesn't matter which direction you put it, it's always the same. So here you can rotate them 90 degrees and have 3 different orientations for the P. The D, turns out, you can have 5 different orientations for it. So you can put 2 electrons in each one of these. You can put 2 here, 2 here, 2 here, 2 here, 2 here. So the D has 5 suborbitals, and it can hold up to 10 electrons. The F has 7 different orbitals that it can have, so it can hold a total of 14. So let's talk about this memory device. If you do not have a periodic table handy, you're going to want to write this down. This is called the diagonal rule. It's based on the Aufbuoy principle, which states that electrons fill from the lowest possible energy to the highest. Okay. Now, take a minute, pause this. I would normally do this slowly in class, but I'm going to go ahead and put it all up here. You can take a minute and pause it and write this down, and I will talk about it here as I go. So each level, you have 1, 2, 3, 4, 5, 6, 7. Each level has an S. Then starting at level 2, they all have a P. Starting at level 3, they all have Ds. 4, they add an F, etc. So each level you add a new orbital type. Now, again, could there be a 5G? Sure, there could be, but we never would get electrons to go in here. We don't just have enough of that. So these are all just theoretical things. So go ahead and write down this triangle if you haven't already. Now, when you are filling things, you're going to draw diagonal lines from the top right to the bottom left. Okay, so that's how you fill them. You start up here. The first electrons are going to go in the 1s level, but that can only hold 2. So when that's done, you're going to fill in the next ones are going to go in the 2s. And when that's full, it can only hold 2. So when that's full, we'll go to the 2p and then the 3s. And then we'll go to 3p and 4s. Then we'll fill 3d, 4p, 5s. Then we'll go to 4d, 5p, 6s. Then we'll 4f, 5d, 6p, 7s. So this is just a way to help you figure out where do I put these electrons. So the first thing we're going to figure out is how many electrons does an atom have. So something like hydrogen just has one electron. So it'll just put one electron in the 1s shell. But something like, let's say neon has 10 electrons. So the first two will go here. The next two will go here. So that's 4. Then the 2p is next, and it can hold up to 6. So 6 plus 2 plus 2 gives me all 10 would be in their spots. Can you have it just if I had what comes after neon? Is it sodium, I believe? Let me look at my periodic table. Yep, sodium. Sodium would have one more and would put it in the 3s. I know, it doesn't make sense until you do it. So let's try and do some here in a minute. Why are the d and f orbitals always lower energy levels? Okay, so when we show you the periodic table method here in a second, this will make a little more sense. But remember, electrons are trying to get to their lowest energy state, as close as they can get to the nucleus, where they don't have to have as much energy. So turns out sometimes they can sneak in a little bit closer, like the 3s. What's a good example? Oh, here we go. Okay, so the F's and the D's, when they come in, we always said F's and D's are kind of weird. So electrons will go to a 5s before they fill a 4d, right? They can just get a little bit closer. They can get a little bit lower energy in the 5s than they can in the 4d. So they'll fill the 5s and then they'll fill the 4d. And they'll even go to the 6s before they'll fill a 4f. So the F's lag like 2 levels behind. The D's lag 1 level behind, which we'll see here in a second. So this is why the diagonal rule is diagonal. If you just follow the arrows, then you'll stay in order. I remember in high school, my teacher taught us the diagonal rule, and I don't know, it didn't click with me. What helps me more is the periodic table version, which I'll show you that as well. So first, let's make sure we know all these different types of orbitals. The s orbital, how many orbitals can it have? Just 1. How many electrons can it hold? 2. The p orbital has 3 different orientations. It can hold 6 electrons. The d orbital has 5 different orbital orientations, so it can hold a total of 10. The f orbital, there's 7 of them, so it can hold 14. So when you're using the diagonal rule, you really have to remember s's hold 2, p's can hold 6, d's can hold 10, f's can hold 14. Now, electron configurations are basically a list of all the electrons in an atom or an ion, and they must go in order. That's the Aufbauer principle. 2 electrons per orbital with that's Pauli exclusion principle. That's the max. You can only put 2 in a thing. And then we need electron configurations so that we can determine the number of electrons in the outermost energy level. That is the valence electrons. Remember, we mentioned those earlier when we were doing Lewis dot structures. The number of valence electrons, that's what's going to determine what an atom can bond to or what they do. All their chemical properties come from those valence electrons. So we're going to write electron configurations. They're going to look like this. So every atom on the periodic table has its own unique electron configuration. So 1s2, 2s2, 2p6. Those superscripts are telling you how many electrons would be in that P or that S or whatever it is. And you just keep going until you have filled in all the electrons for whatever atom you're doing. So this number in the front, that's your energy level. So this is energy level 2. The P is the sublevel, your orbital, right? And then you have how many electrons you put in it. So in this case, if you have 2p4, this is something that has 4 electrons in the p orbital on level 2. Okay. No, now p could hold up to 6, but this only has 4, so it obviously we will be able to tell what it is. I'll show you that here with the periodic table soon. But first, let's just try it. Now, I am going to go to my Jamboard here. Hold on. Oh, there it is. So again, you can use the diagonal rule that you have in front of you because you wrote it down, right? Or if you have a periodic table, you can go and look at your periodic table and think of it like this. So we mentioned this the other day in the lesson. Your periodic table should be like this, but we make it look like this so that it fits on a sheet of paper for you. But this block, this is the S block. Notice it's 2 blocks wide, right? This is the P block. You'll notice it's 6 blocks wide because guess what? P's hold 6, right? The D block right here is 10 blocks wide, and the F block is 14. Those aren't accidents. It's put together this way for a reason. So if you're using the periodic table, you can just start at the top and keep working your way over until you get to whatever element you're looking for. So if I was doing hydrogen, I would just start here and say, oh, it's right here. Here's hydrogen. There is 1 electron in the 1s orbital. So I would just write 1s1. If I were doing helium, I'd still be in the 1s. I know it's over here. Helium's kind of the black sheep of the family here. Should be here as far as orbital diagrams go, but there we are. It's over here because it's also a noble gas because it has that full shell. Because it only takes 2 to fill that shell, right? Level 1 just has an S, 2 electrons, and it's full. So for helium, it'd be 1s2. If I were going to do something like sodium, sodium's right here on the periodic table, I would say, okay, it has 11 electrons. Let's start at the top and work our way over there. 1s, that'll hold 2. Then I'll go to 2s, that'll hold 2. Then I'll go to 2p, which can hold 6. And then I'll be at the 3s. And since sodium's right here, I'd stop right here and call it 3s1. Okay, so I can't have all of these things on the screen at the same time. So hopefully you have put notes on your periodic table to mark the S block, the D block, the P block, the F block. Notice that the F blocks are 2 levels behind. So, and the D blocks are 1 level behind. So even though this is level 4, this is a 3D. And even though this is level 6, this is a 4F. Remember, if you look at the numbers, you'll see this number, there'll be a big jump between here and here. That's where the F block goes, okay? So let's give it a shot. All right, we'll start with hydrogen. We already said, let me pull up periodic table here. We already said hydrogen's right here, so that's in level 1, S block. There's only 1 electron in it, so easy enough. Oops, that's the wrong thing. 1, uh-oh, my pen. 1, S, 1. There you go. That was easy. Let's look at lithium. Where's lithium on the periodic table? It's right here. So 1s is going to be full with 2, and then I'm going to go to the 2s, and it'll stop right here because it's only got 3 electrons. So the last thing will be 2s1. So, sorry, 1s2, 2s1. Let's try nitrogen. You go ahead and stop and try it, and then compare to my answer. Nitrogen's right here. There's 7 electrons in it. So I'm going to go through the 1s, then the 2s, and then I'm going to go to 2p, and it'll be the third. So I'm going to write 1s2, 2s2, 2p3. So that's 3, 4, 5, 6, 7 electrons, and that's how many nitrogen has. If you were using the diagonal, you would start here. Again, you're just doing the same thing. The 1s, remember it holds 2. The 2s holds another 2. Then I put 6 in the 2p, and then I was at the 3s. Just keep adding up your electrons until you get to what you need or where you need to be. Why do I keep opening up my to-do list? Okay. Let's do neon. So go ahead and try it on your own. Pause and then come back and do it, or I'll do it too. So neon is right here. It's number 10. So it's got 10 electrons to place. So let's place them. 1s, 2, 2s, 2, 2p, 6, 6, 7, 8, 9, 10. Yeah, put them all in. Go ahead and try the rest of these and then hit pause, and I will come back, or when you're done, come back and compare them with mine. There's potassium right here. So I'm going all the way to 4s on this one. There you go. I'm going to get a paper periodic table in front of me real fast to do zinc. Oh, I guess I'll show it on here too. Where is zinc? Right here, number 30. So we're going here. Now we're picking up into that D block. And we have to remember the D is one level behind. So this is 4s, but this is 3D. So let's go ahead and do that for zinc. And 3D, it's the last one, so 3D10. Run out of room here. Okay. And then the last one is PB. Oh my goodness, that one's going to take forever to write. And I'm going to need way more space. So I'll go for it. And here we go. Just to demonstrate that there must be a better way, right? So PB, it's all the way down here. I got to put 82 electrons in this thing. Oh, that's crazy. So let's do it the long way, and then we'll learn a shortcut. I'm going to get a new slide just to give me some more space. So PB. Okay. And then we got 3D 10. Okay, and after 3D10, remember we're not done with level 4, so we go 4P6. And now after 4P, I go to level 5, so I have 5S2. And then again, we're at the D block, so I'm going to do 4D, and there'll be 10 of those. And then remember, we're one level behind on the D blocks. And then we'll be back at 5P6. Then we're going all the way down to level 6, where I've got 6S2. Now, things get funky here with the D's and the F's, but this whole D and F is full. So we will start with, let's go down and grab the F's. So remember, F's are 2 levels behind, so 4F, and there'll be 14 in there. And then we'll come and get the D block, which is one level behind. So it's 5, D, 10. And then after 5D, we're back at 6S. Sorry. And we're going to stop at, I'm sorry, did I put 6S at 6P? And we're going to stop at the second one, so that's 2. Now, there's no way. You know chemists are lazy. We don't like to write all this stuff out. There must be a shorter way, right? This is what we, how we did with the Lewis dot structures. We said there's got to be an easier way. So let's go look at the easier way. That is what we call the long version. It puts every single electron in its home and gives us the address for everyone. But you and I both know all we really care about are valence electrons, right? So hopefully you have your periodic table notes like this on it. And if not, you should take a second. Hopefully you have a paper periodic table, pause it, and write some notes on it so that you have this. Now, shorthand version. This is the shorthand version. This is because all we really care about are those valence electrons, right? Those outermost ones. If we know that everything in the core is completely full, then why do we write it, right? So let's show the shorthand version of how to do this. We're going to use the last known full noble gas and then start finishing it off. Okay, so how does that happen? So step 1, it's Showcase Showdown. Find the closest noble gas to the atom or ion without going over. Okay, so these are the steps. You might want to pause, write these in your notes before we get into it. You're going to put the noble gas in brackets. Okay, so that's going to be the step 1. Put the last noble gas in brackets. Step 2, pick up from there. So where are you going to resume on the next level? This is where the diagonal rule kind of leaves you stranded, and you're going to need that periodic table. And then step 3, resume the electron configuration until you are finished, until you hit whatever atom you're going to. So let's take a look at something like chlorine. This would be the longhand version of chlorine, okay? 1s2, 2s2, 2p6, 3s2, 3p5. And you're ending up like right here with chlorine, right? Now, all of those levels before it were full, so we don't really care about them. We only really care about the level you're on. So when we say go find the last noble gas, that's what you do. You go up to the last level and over to the last noble gas, which in this case, right here on your periodic table, is neon. So you put neon in brackets. Then you just pick up from there. What comes after neon? Well, after neon, I'm in level 3, block S. So I'm in the 3s, which will hold 2, and then I'll go to 3p, which could hold 6, but I'm stopping at chlorine, so 3p5. So instead of writing all of this, you can just write this. That neon in brackets replaces the electron configuration for up to neon, okay? Because we don't need to know all that. We just really care about this outer stuff. That's what's going to affect where things go. All right, let's try a few shorthand. You ready? So let me go back to my Jamboard. You'll find shorthand much easier. Excuse me, I had a little hiccup. So let's start with chlorine. We just did. Let's go to potassium. So let's look at potassium on our periodic table. Here's potassium. If I were going to do it the long way, I'd start with 1s2, 2s2, 2p6. But the shorthand version, I just go up a level and all the way over to the last noble gas, which in this case is argon. So argon's going to be in brackets. And then I'm going to start at 4s, and potassium's right there, so it's just 4s1. So instead of writing out the whole thing, I could just write in brackets argon, and then 4s1. That's it. For calcium, again, take a minute, pause the video, you try to do the rest, and then you can unpause and watch me do them. So let's do calcium here. Here's calcium. The long way would have me going 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, right? But shorthand version, I go up all the way over, get argon, and then I come down to 4s, and there's only 2. So for calcium, it's so hard to write brackets for some reason. Ar 4s2. I'm getting better at this writing on the tablet thing now. And then there's I. Let's look where iodine is. It is all the way over here. So, oh my goodness, I would have to do all of this stuff to get there. All 53? No way. I'm just going to go up and get krypton. That's going to be my last one. Krypton in brackets. And then start at level 5 for 5s2, 4d10, and then 5p, stopping here, would be 5. So let's write that out. I need mine in front of me here. So brackets KR. And then below that we've got, sorry, I got to post it on my thing. 5s2. And then 4d10. And 5p5. And the last one here, bismuth. So look at your periodic table, try to do it yourself, and then unpause and watch me. Oops. Now I've still got those F's and D's I got to keep in here, so. And then that was 5D10. And then bismuth is the third one in 6p, so 6p3. My goodness. So we've learned a lot today. Hopefully you are able to write electron configurations, either the long version or the shorthand version. And good luck. Let you know how to get a hold of me if you have any questions, and you'll have some practice on this. Have a good day.